Hi, I'm Grace, and today I'll be talking to you about communication optimal tilings for projective nested loops with arbitrary bounds. So for motivation, we have a large variety of applications, so things like convolutions, matrix multiplications, tensor contractions, and the like. All these algorithms can be written as nested loops accessing arrays, and we'd like to optimize the communication complexity, that is, how much data we move around, for all these algorithms, since the cost of communication is often more expensive than the cost of computation. We want something that's relatively automatable, we don't need to do hand tuning for each one, that applies to many different algorithms, and something that will give us a theoretically optimal solution. So more formally, we'll be looking at D-nested loops indexed by x1 through xd, which are bounded by L1 through LD, performing operations on n different multidimensional arrays A1 through AN, indexed by functions phi1 to phi(n). So something looking like this matrix multiply case here. We'll be restricting our attention to the case where the phi's are projections. That is, they return subsets of their inputs. So for instance, this phi takes x1 through x3 and returns x1, x3. And what we'll try to do is minimize communication between a CPU hooked up to a cache of size m and slow memory. Most of the existing work on this subject that we build on has operated as follows. We're going to split our program into a bunch of tiles, each of which is defined as a set of instructions where we consume exactly m words of memory movement. So if we get an upper bound on this tile size, then the number of tiles we need to do is at least the total number of operations, that is the product of the Li, divided by the upper bound of the tile size. And if each tile uses m words of memory, we multiply this term by m. This gives us communication lower bound. And prior work has expressed this, has found an upper bound of the tile size through this particular HBL linear program, which we write here. Unfortunately, there are a couple of disadvantages. One, the tile size may not, the tile given by the linear program may not fit in the problem itself. For instance, if you have a matrix multiply problem, classical results will tell you that a root m by root m tile is optimal. But what if your matrix is really tall and skinny? You can't fit the tile inside the matrix. So, prior work has mostly focused on cases where you can assume that your tile will fit inside your problem, that is, the loop bounds are large. What we do is focus on algorithms that work for arbitrary problem sizes at the cost of only focusing on projective phi. So here's our main theorem. What we have is a communication lower bound for every single set of indices, here 1 through q, that we say are small. So we actually get 2 to the d different lower bounds, one for each composition of this set, so we can permute the loop indices any way we want. And what we'll do, in order to get this, what we'll do is we'll perform sort of the linear program, the HBL linear program, that analysis on each slice and sum them all up. So now this is a really complicated expression, and worse yet, we have exponentially many terms. So in order to actually achieve this, what we also show is that you can both find this lower bound and achieve it by sort of doing the obvious thing with a tiling. So what you do is that you guess that the tile is a hyperrectangle of size b1 through bt. We want to maximize the tile volume, So the tile volume is the product over I of BI, subject to memory constraints, that is, the addresses touched by the tile must fit inside memory, and loop bound constraints, that is, BI must be at most Li. So we take the log to get a linear program. It looks like this. And we show through a duality argument this tile has cardinality equal to one of the upper bounds of the tile size given the previous slide. So we achieve a communication lower bound. So here's an example. Suppose we have an m by n by k matrix multiply. If you just write down the linear program without the tile size constraints, what you'll get is sort of this classical 1/2, 1/2, 1/2, or root m by root m by root m algorithm or tiling for matrix multiply. But if one of the dimensions are small, you can find out that the lower bound in this case is actually the size of one of your input matrices. It's kind of obvious, but what it does show is that this term here, which you get by sort of performing this LP for every set of, for all possible small indices, is a complete expression for the communication cost of communication optimal matrix multiply. So what we've done is shown that you can actually find these communication optimal algorithms or tilings that achieve the lower bound. For this set of projective problems, what we'd like to do is generalize it to larger classes of problems, such as convolutions, test it as a compiler optimization, find constant factors rather than just asymptotics, and to automatically generate parallel algorithms and data flows. The latter two have already been done for large indices, and we'd like to extend it for small indices. Thank you. Briefly scroll past the references, and I'll be on Slack to answer questions. Thank you again for listening.